Hey everybody, I hope you're doing well. In this particular video, I want to talk about the angle of elevation problem. So I have this written out in a Mathematica file. We're not going to use Mathematica, but here's the statement of the problem. I have two people that are on roof of buildings that are separated by a road that's 25 feet apart. One person is 100 feet above another, but the person that's above is going to drop a rock. And the person that's below is going to look at the rock, and as it comes down, we're going to measure how fast the angle between their eyesight and the horizontal is changing. And we're going to do this in two different scenarios. One where the rock is 25 feet above person B, and the other one where the rock is 65 feet below person B. So let's see if we can put this all together in a nice picture. So over here, I am going to have building A or person A, and I'll draw a little tiny stick figure here. And they're going to take a rock and they're going to drop it down here. And person B, well, they're going to be on another building and they're going to be 100 feet below. Now, this 100 feet doesn't come into play, but there's a moment in time where this rock is 25 feet above person B. So this distance right here is going to be 25 at one moment in time. So what I want to do is look at this angle that's right in here, and I'm going to call it angle alpha. So what do I know about this? This distance from here to here, and yeah, I'm drawing the rock a little bit away from the building, but essentially it's going to go right down the side of it. This distance right here is always going to stay at 25. And this distance here, well, that's going to change, so I'm going to call that y. So what do we know in this problem? Well, we know that dy dt, this is going to be equal to -3 because the rock is falling at 3 feet per second. Now you may be wondering if this is realistic, and the answer is no, it is not realistic. I'm choosing a constant rate of fall at 3 feet per second, and I know that's not realistic. I'm using that to make the calculations a little more simple. And what we want in this problem is what d theta or d alpha dt is. This is going to be measured in radians per second, and this one is in feet per second. So how do I get a d alpha dt out of this picture? Well, a nice model for this is tangent. Tangent of alpha is opposite over adjacent. Opposite over adjacent. Y over 25. Now I like to write this without the fraction, and I can write it like this. Taking a derivative of this model, I wind up getting 25 secant squared of alpha, d alpha dt, is equal to dy dt. I already know what dy dt, my goal is to figure out d alpha dt. So I have to figure out what secant squared of alpha is. If I can figure out what secant is, I can just square it and figure out what secant squared is. Well, secant, if you think about secant, secant is the reciprocal of cosine. Cosine is adjacent over the hypotenuse. I'm going to call this capital H just for the moment. So I'm going to look at the hypotenuse over 25. The hypotenuse squared, I'm going to use the Pythagorean theorem here, is equal to y squared plus 25. But specifically, when we're doing this at y equals 25, that's my big goal here, is to make sure I'm doing this at a specific moment in time. I wind up getting h squared is equal to 2 times 25 squared, or h, is equal to 25 root 2. That tells me at this moment in time that secant of alpha is equal to root 2. Now secant squared is just equal to 2, and that is really, really nice. I'm going to make that substitution. And I'm going to substitute in -3 for dy dt as well. So this gives me d alpha dt is equal to -3 over 50. And again, remember, this is in radians per second. So this is the answer to part A. So I'll make this a little bit bigger so we can see this. Now part B is very, very similar. The difference between part A and part B is that the rock is 65 feet below person B. So I can use some of the same techniques, actually almost the same exact equations, to deal with part B. So the difference here is that now the rock is down 65 feet below, so I'm going to look at this angle right here. And let me call this angle beta in there. So for part B, my model for part B is going to be tangent of beta. Well, it's still opposite over adjacent. And I just need to label this distance here. I'll call this y yet again. So we're going to deal with y over 25. So my model for part B is going to look something like 25 times tangent of beta is equal to y. Taking a derivative of this, I get 25 secant squared of beta d beta dt is equal to dy dt. Again, I need to figure out secant squared, but if I go through the same thing here, I'm going to wind up getting secant of beta. Well, that's equal to, I'm going to call it h again. I'll call this h over here, over 25. But h squared for this case is equal to 65 squared plus 25 squared. It's a little bit different than what we had before. So really quickly, let's go into Mathematica and do a quick little tiny calculation of this. So if I go down here, I'm going to take a square root of 65 squared plus 25 squared, and I wind up getting 5 times the root of 194. So in this particular problem, h is going to be 5 times the square root of 194. So secant of beta is 5 root 194 over 25. Or I can say root 194 over 5. But I'm going to square this whole thing when I put it in here. 25 times this thing squared. 194 over 25. Oh, that's really nice. The 25's cancel. Times d beta dt. And that's equal to dy dt. These are going to cancel. So d beta dt is equal to, well, I have never figured out what dy dt is. Up here I said it was -3 feet per second. But that doesn't make any sense. For this particular part, dy dt, this is equal to 3 feet per second. And you might be thinking right now, but the rock's still going in the same direction. But y doesn't measure the velocity of the rock. Y is getting larger as this rock goes down. So this better be positive. So this dy dt is 3, and I'm going to divide it by 194. So this angle beta is getting larger. Well, that kind of makes sense. And again, this is in radians per second. So part A and part B. I hope you found this useful. If you have any questions, let me know. Have a great day.